gaseous mixture with a molar analysis of carbon dioxide coming into a reactor that's 10%, a heat exchanger. The mole fraction of carbon monoxide coming in is 80%, and the mole fraction of just oxygen, O2, coming into a heat exchanger is 10%. And it comes into this heat exchanger, and then it goes out of that heat exchanger. Inside the heat exchanger, it is heated. So there's a Q dot into this gas mixture that's going into the heat exchanger. It's heated at constant pressure. And an equilibrium mixture of carbon dioxide, so CO2 exiting, the mole fraction of carbon monoxide exiting, and the mole fraction of oxygen exiting. These are unknown, but we know that it's in a state of chemical equilibrium when it exits. And we know we're given that the temperature at the exit is 3,000 Kelvin, and that the pressure is 3 atm. It's also 3 atm on the inlet. It's constant pressure, so it's negligible pressure change flowing through that heat exchanger. So we're asked to determine the molar analysis of the exiting mixture. We're asked to solve for these mole fractions. Okay? So we recall, if it's in equilibrium, the combination of the first law and the second law, we have an equilibrium constant for that reaction. We can write it something like this. K is equal to, either in terms of mole fractions or amounts. Because I have limited board space, I'm just going to write it in terms of amounts, N's. So we'll talk about the number of moles. I should write down the reaction equation, shouldn't I? CO2 dissociates to produce carbon monoxide and 1/2 oxygen. All right. So the number of moles of the carbon dioxide exiting, raised to the 1 power, the number of moles of the oxygen exiting, raised to the 1/2 power, divided by the number of moles of the carbon, I messed that up, didn't I? It's carbon monoxide exiting, and carbon dioxide exiting raised to the 1 power. Then we have the exiting pressure divided by 1 atm, which is the reference pressure, divided by the number of moles total. The number of moles total is the number of moles of carbon dioxide, number of moles of carbon monoxide, and the number of moles of oxygen all exiting. And this is raised to the 1 plus 1/2 minus 1 power. And so that just goes to the 1/2 power. So how do we solve this problem? It's preferable to solve it in terms of n's. And once I solve for those n's, let's write it up kind of over here, the number of moles of CO2 exiting. If I can solve for that, and I can solve for the number of moles of CO exiting, and then I'm having a hard time writing things today, the number of moles of O2 exiting, then I can sum them up. I'll get the total number of moles exiting, and then I can back up and I'll say, well, the mole fraction, the molar analysis, my final answer is going to be the number of moles of CO2 exiting divided by the total number of moles exiting. Likewise, number of moles of CO exiting divided by total N, number of moles of O2 exiting divided by total N. See how we do that? So I prefer to work in terms of N's. Okay. So is this good? Where did this equation come from? That equation came from equilibrium considerations, combination of first law, second law. We didn't derive it, but most people, if they've had a chemistry class, have seen something like that before. Now, we look at it, we have 1, 2, 3 unknowns, and we need to then solve for these unknowns. With one equation, it's impossible. We need additional equations. We have already used first and second law in equilibrium with the cake. Now we need to go to a carbon balance equation. The first time you do this carbon balance, you need to go slow, but once you get the hang of it, it's like, oh, okay, I understand. You have what comes in must equal to what goes out. Is that true? Right. So what we do is we assume that the total number of moles coming in is 1 kilomole. It seems a little silly doing this, but if that's true, then the number of moles of carbon dioxide coming in is 0.10 kilomoles. And the number of moles of carbon monoxide coming in is 0.80 kilomoles. And the number of moles of oxygen coming in is 0.10. It's almost too trivial of a step, but do you see the utility of that? So now I'm talking about just do everything on a 1 kilomole total gas coming in to that heat exchanger. And so I could say, well, how many moles of carbon are coming in? Well, I'm going to have 1 carbon for every CO2 in. And I'll have 1 carbon for every CO in, and I'll have none for the oxygen in. That makes sense. So, substituting numbers, this is 1 times 0.1, 1 times 0.8. And so what flows in is I have 0.9 kilomoles coming in. That's how many carbon have to go out. So the in's equal to the out. Well, I do the same thing on the exiting. I say, well, I don't know how many moles of CO2 exit, but for every mole of CO2 exits, there's going to be 1 carbon with it. Likewise, there'll be 1 carbon with every CO that exits. So this may seem almost too trivial, but there is an additional equation. It's from our carbon balance. What we're going to do is follow the strategy developed in the textbook, which says I'm going to try to take 3 equations and 3 unknowns and reduce it to 1 equation with 1 unknown. And what I'm going to do is I'm going to pick the unknown to be the number of moles of CO that exits. I'll let that be the symbol Z. They picked Z. The book could have used L or P or A or anything else, but I'm trying to be consistent with the book. So this equation right here can be rewritten as the number of moles of CO2 exiting is equal to 0.9 minus Z. So anytime I see the number of moles of CO2 exiting, I can substitute. So this equation here, I'm going to rewrite it to get 1 equation with 1 unknown. It'll be, let me do it this way. 0 equals to K minus the number of moles of CO exiting, that's Z, raised to the 1 power, divided by the number of moles of CO2 exiting, raised to the 1 power, 0.9 minus Z. See that? And then we're going to have 3, and then it's going to be tough, but I'm going to try and put all these in here. I'll have 0.9 minus Z for the number of moles of CO2 plus Z for the number of moles of CO. And I now need to do the oxygen balance. I need to scoot down just a little bit for more room. We'll do an oxygen balance. The ins must equal to the out, okay? So if I have the number of moles of CO2 coming in, do they bring any oxygen? If it does, how many for each mole of CO2? 2. Okay, the number of moles of CO coming in. If you have some CO coming in, for each CO coming in, there's 1 O. And for the number of moles of O2 coming in, I'll have 2 O's. Do each of those make sense? So we had 2 times 0.1 plus 1 times 0.8 plus 2 times 0.1 all coming in. So that's 8, 1.2. So this is 1.2, right? That's what's coming in. Even though I only have 1 kilomole of total gas coming in, I have 1.2 kilomoles of oxygen coming in with it. All right. So what's coming out? Well, it'll be the same thing. the number of moles of CO2 going out. For every one that goes out, there's 2 oxygen with it. The number of moles of CO exiting times 1 plus 2 times the number of moles of O2 exiting. Well, what I do is I say, 2 times number of moles of CO. Let me substitute 0.9 minus Z. It's a little bit of algebra, isn't it? Number of moles of CO, that's Z times 1, plus 2 times the number of moles of O2. I need to scoot down a little more. So with this equation, I'll pick up 1.2 equal to 1.8 minus 2Z plus Z plus 2 times the number of moles of O2 exiting. So the number of moles of O2 exiting will be negative 0.6. That'll be plus Z divided by 2, or Z minus 0.6 divided by 2. Did that make sense? Did you follow that? Now we can substitute that up here as well. So we need to substitute for the number of moles of O2. It'll be plus Z minus 0.6 divided by 2. All that was raised to the 1/2 power. And then right here, we're going to have, for this term, we'll have Z minus 0.6 divided by 2 square root. Why the square root? Because of this 1/2 power. Now you're ready. Now you have one equation with one unknown. It's a combination of the chemical equilibrium equation right here, plus the oxygen balance, plus the carbon balance. And so we substitute. How do I solve for Z in this equation? How would you solve for Z in that equation? Learn how to do it with your hand calculator that you can use in the exam. So a TI 30 or something like that. This is recorded last semester, and you could go to this lecture around 58 minutes. What I did was I set up this equation where there's the K and there's a Z to the square root, blah, blah, blah. It looks just like the one we're solving, but it's not the same equation. And with this calculator that I never use, but it's the TI 30X or X Pro, which is some of you may have. These are the keystrokes to set up and to solve that problem. And that was set up by somebody you may know, Jeffrey. And the next one was set up, same semester, another student, Sung. So he set it up. After that, he showed me how, look at, I think I can do it in fewer keystrokes. So it's not like there's only some keystrokes that work. There's different ways to set it up and to solve it with the same calculator. Okay? These are both available on that lecture. It's just around 3 minutes. So I encourage you, if you're brand new, and so both of these students are very helpful. As well as you can come by my office. I don't use the TI. I use the HP Hewlett-Packard, which is that's an approved calculator for the exam as well, the HP 35. As well as contact John Delgado. He helped students last semester and the semester before get prepared to use their calculators to solve. Okay? Does that make sense? One thing I thought I would do is just show you how I would solve it in Excel. So you set up the equation such that you have an unknown Z, and that Z is changed to iterate. Okay? And so I set it up so I get the number, if I was no Z, let's just change it to some number. Give me a minute, please. Let's say this Z is not this is the final answer right here, 0.614, but we don't know it, so we think it's 0.7. Well, if it was 0.7, then the number of moles of CO2 exiting would be 0.9 minus Z, and the number of moles of O2 would be Z minus 6 over 2. So it'd be these numbers. Hence, the total number would be 0.95. The equilibrium constant, knowing that getting the value out of the table A25 is K right here. And so this function of Z, which is just typing in that equation. So you would do the same thing in your calculator. Type that equation in. Okay? And then if you're doing it in Excel, if you've never used, go under the Data tab right here. Then look under Data Tools and find the What If analysis. If you pull down on that, you'll find this function. It's got a funny name, but it's called goal seek. And the idea behind goal seek is I have something and I want to drive it to another value. So in terms of goal seek, it says, okay, what value is your set value, set cell? So cell C7, I want to set it to a value of 0. I want to drive that value to 0. By changing what cell, I'll iterate on that cell. So everything, if I change cell C2, it changes it. And so you hit OK, and it works it. A lot of times what I have to do is, that's close to 0, but maybe I'll take that function, multiply by 1,000, so I moved it over, and I'll just redo this, setting to 0. If you notice, it's 0.614 with something. Let's just do that again. Under Data, What If analysis, goal seek, now set cell C8 to 0 by changing the same cell C2. Let's see if that cell changes any. It changes, but very little. Okay? And so that's one way to sort of trick Excel to really drive it to 0. So then I came down here and just copied and pasted and said, well, if Z is this value right here, which I can even go back and grab that value from Excel, then the final answer for this and the final answer for that, the total number of moles, and then I could calculate the mole fractions. The mole fraction is equal to the amount of CO divided by the total amount, and that gives you the same number. Okay? To put it in percentages. Move it over. Okay? Can't use Excel in exams, but the same principle. I think if you know what you want to achieve with your calculator, then you'll be better equipped. So back to our lecture.